Photoelectric effect. Okay, this is, see, photoelectric effect is, see, most of physics or most of the science has evolved based on some experiments, and some of the experiments are what you may call as landmark experiments. They gave a new insight into nature's behavior. So photoelectric effect, let's understand photoelectric effect. The word photo indicates it has got something to do with the light, and electric is something to do with the charge. So this gives a relationship between light and uh, electric effect. So even before this topic, we have gone through the topic of EM waves. EM waves, based on Maxwell's proof and other experiments, it proved that light is a form of a wave. What kind of wave? It is electromagnetic wave. Electric field and magnetic field oscillate, which creates light, any form of EM wave. So that was understanding, and then some more experiments were conducted. It was something like this. Those experiments were about electron emission. Let's understand what does electron emission mean. See, we know, we have some understanding of metal. What are the primary property of the metal? When we talk of metal, the primary property of the metal is there are a lot of free electrons. Practically every atom, there's one free electron is released, and that free electron can move around within the boundaries, and it can move within the boundary of the metal surface. It normally, but it can't normally escape metal boundary or surface, because as electrons tries to escape, see, just think of it. So if I have a metal, whatever shape the metal may have, and if I have metal, and if electron tries to escape, if electrons come near the boundary, so since overall it is neutral, rest of the objects, these electrons are trying to escape. So rest of them, ions will develop, this will develop a positive charge, it will try to pull it back. So normally electrons cannot escape the metal surface of boundary as positive charges pull it back. That's normally what is not happens. So though there are free electrons, they do not, they remain, they keep moving around, but within the boundary of the metal. Then we see, can they not escape at all? No, they can escape. They are free. But something like this you would have done in case of gravitation. We study something like escape velocity. What is escape velocity? So if we give them high enough kinetic energy, they may escape. Something similar happens in case of gravitation. Any mass is not able to escape Earth's gravitational pull because gravitation is trying to pull it back. Something similar here, positive charge is trying to pull the electrons back. But if we give it high energy, it will escape. So that is something we define in form of work function. Let's understand a simple definition of work function. What is work function? A minimum amount of energy required by the electron to escape the metal surface. Okay, if they acquire this kind of energy, this kind of kinetic energy is required, then with that kinetic energy, they can escape. It is something like escape velocity, energy associated with escape velocity, something similar. And this is work function, this minimum amount of energy required. And this will depend on surface to surface. Some metal may require lesser quantity, some metal may require more quantity. And this, since we are talking about energy of an electron, is such a small particle. So energy also is small, and those small energy we measure in terms of electron volt. What is electron volt? See, we know what is energy. Energy is equal to charge into volt. If charge is 1 coulomb, then volt is 1 volt, then energy becomes equal to 1 joules. But if the electron, so if it is E here, rather than I have to substitute value of charge of an electron. 1 electron volt is equal to 1.6 into 10 to the power minus 19, which is charge of an electron, so many joules. Volt is volt. So if we see coulombs volt becomes equal to joules. So 1 electron volt is a very small unit of energy. 1 electron volt is equal to 1.6 into 10 to the power minus 19 joules. And this is commonly used in atomic physics, so we'll keep this in mind, and it's pretty simple. So it is EV, so just this term is equivalent to charge of an electron. Okay, work function. And what is the value of work function? As we said, for different metal, different value. So this is a kind of table. So what we notice here, there's cesium, this has lowest work function in the range of something like 2.1. And this work function is defined only for metals. There only electrons are free. Where it is not free, it requires much higher energy. So what we notice here, from lower end is something like close to 2 electron volts. upper end platinum more than 5 electron volts. Okay, so this is kind of energy electron needs. If they have energy greater than this, it will escape. If it has less than this, from cesium surface, this minimum energy it needs. For anything aluminum, it needs energy equal to 4.2, almost twice the energy for it to escape. Okay, and so what are the ways of to make an electron escape a metal boundary? We have to provide energy, and energy can be provided by different means. The different physical process may provide that energy. What are those physical process? One you call as thermionic emission. And this word therm, moment the word therm has come, I think most of you can guess what a thermionic emission mean. We provide energy in form of heat. We heat up the metal. If you heat it up to high enough energy, what will happen is the kinetic energy will keep on increasing as we heat it up, as we have done in case of kinetic theory of gases. Free electron also is like electron gas. So they may acquire adequate energy and they may escape. That's one. And it's also field emission. Anybody recalls about something related to field emission? We have talked about dielectric breakdown. And this is also something similar. So when you apply high enough electric field, that also provides energy, and the energy provided, if field is high enough, what kind of order of field is required? At something the order of 10 to power 8 volts per meter. And you notice, I think we have mentioned earlier also, whenever see a kind of lightning, see in case of lightning, whenever see that lightning or spark, that is the spark is due to a flow of electron. So those who have seen spark plug, some of you might have seen spark plug. Old vehicles used to have spark plug. Spark plug also we provide potential difference, but space between, see something spark plug will have two metals at very close spacing. So if voltage be constant, if spacing is made very small, the field becomes large. The spark plug was a device which was commonly used to provide what you may call as free electrons. An electron will flow, and whenever electron flows, it appears, we see that spark, we see that light effect. So this is also a strong field. And third, that is the topic for, this is related to this chapter here, photoelectric emission. What does photoelectric emission mean? Here, energy is provided by light. Light provides energy. It means this experiment demonstrated the light, when it falls onto the metal surface, light carries energy, and that energy, when the light falls onto the metal surface, can be transferred to free electrons. That is photoelectric emission. Energy transfer from light to free electron, and if the energy is large enough, electron can escape. So suppose I have calcium, and in case of calcium, the light has to provide an energy of 3.2 electron volts or greater for it to escape. If we provide 3.2 electron volts, it will escape with minimum kinetic energy. If we provide greater than 3.2, it may escape with more than small kinetic energy. So this is our topic. This is about emission of electron from the metal surface when the light falls onto the metal surface. That is photoelectric effect. That's what you're going to study. And this is most of the learning from this chapter was based on several experiments conducted by these people, Alvak and Leonard. They conducted several experiments, and they summarized those experimental observations, based on which we got a better understanding of what happens in case of light falls onto the metal surface. And we have seen different type of metal surface. Let's see, this was the kind of experimental setup. Let's first try and understand what is the experimental setup. It is evacuated glass tube. Why it is evacuated? If it is not evacuated, there will be some other molecules also present, and because of those molecules, electrons will collide and they will lose energy. It is evacuated so that other than electrons which are emitted because of photoelectric effect, there's nothing else inside the tube. Okay, so let's look at one by one. And this is one plate here. So this is metal plate. And this arrangement, we make an opening here, and there's a light source. Light can be made to fall on the metal plate. And if the light carries enough energy, what will happen? Electrons will get emitted, and electrons are free to move within the boundary of the tube here. We provide these two ends. One you can call anode and cathode. They are connected to a battery, and there's a commutator. Purpose of commutator is either we can make this as higher potential, or we can make this higher potential. It is possible to make any of the two plates at a higher potential. So we can make the photoelectric plate at a higher potential, or we can make other as a higher potential. So let's see what this happens here. So if how do we check whether electrons are getting emitted? Electron is not something we can see with the eye. Either we can see in terms of spark. Spark happens because these electrons collide with the air molecules. Since it is evacuated, we won't see the spark. So one way of understanding is the right pause, electrons get emitted. Since this is a negative charge, if I keep this plate as positively charged, what will happen? All electrons which are emitted will travel from here to here. It will reach the plate. So even though there's a gap between the two plates here, normal case, what we expect when there's a gap here, which is like infinite resistance, loop is not complete. But if the electrons can flow from one plate to other, what we'll find, the loop gets complete and we see the current flowing in the circuit. And there's a small, what you may call like a galvanometer. It can detect that small current. So whenever there's a electron emission here, we can see a small deflection in the galvanometer. So we can measure how many electrons are getting, at what rate electrons are getting emitted by the way of measuring the current here. And there's a battery here and there's a commutator. We can change the voltage between these two. We can change the potential difference. So what are things in this arrangement? It's a vacuum tube. We can have a light source. With light source, we can change the type of light we use. We can change its frequency. We can use red color. We can use blue color, different colors, different frequencies. We can change the intensity. We can change the voltage between the two. We can measure the current here. This is the kind of arrangement setup. So all these parameters, relevant parameters, can be varied. Let's see what are the series of experiment, what the findings are, and those of based on those findings, what is the conclusion we come to. And this was what you may call as, this was really a landmark experiment, phenomenal experiment, which gave great insight into several new things which could develop later. So evacuated to avoid loss of kinetic energy of electron. And there's arrangement to vary potential between C and E. Where is the plate here? So we can call this plate as, typically we call this as a collector plate. Collector plate, you understand why it is called collector plate? Electrons will come and get collected here. So this is collector plate and this is photosensitive plate. Light will fall. Here the emission will take place and electrons which are emitted may get collected here. And if emission and collection is happening, it will lead to current. Are we okay with this? Emission and collection, if both are happening, it will lead to current, and more number of electrons getting emitted in unit time, the current will be higher. So, and we can vary this potential. Okay. So if A is kept at a positive potential will attract electrons emitted at C. That's what the positive potential will do. What are the factors which are which we can study here? We can change the frequency of light. Can someone tell how do we change the frequency of light, or how do we change the wavelength of the light? Can anybody think of a way? How do we control the wavelength or frequency of the light here? Can anyone think of a method to change the frequency or wavelength? Anyone? Can anyone think of? See, you all understand. See, red color has a different frequency. Blue color has a different frequency. Violet color has a different frequency. Among all the colors, all 7 colors, which color has highest frequency? Does anyone remember which color has highest frequency?
Red. Red.
Actually, red color has lowest frequency, highest wavelength, and violet color has highest frequency. So here also what you can do, see, if I want only frequency related to violet color, how do so what I need to do, you know, the white light has multiple colors. So you can, one simple way, I can use a prism. And what does prism do? Even the white light which is coming, it separates into different colors. So if I pick up only, so what you can do, it separates light into different frequencies, wavelength. So with this, I can pick and choose a particular frequency or particular color. And that's kind of arrangement. The frequency we can control. Potential difference between plates can be controlled because of battery, and there's a variable resistance here. And what are we studied energy of electron emitted, and this is really interesting. How do we find out energy of electron emitted? We'll see. And intensity of radiation. Well, how do we study intensity of radiation? Suppose I have a source of light. You know, there's something called sodium lamp. Sodium lamp emits EM rays of something like yellow color. It's a monochromatic source of light. What will happen if I move the source nearer to this plate here? If the distance becomes half, we have seen earlier, if this is a power source, intensity, distance becomes half, intensity becomes 4 times. Intensity is varies as 1 by r square. We can change the intensity and we can change the plate also. As see several metals, we can replace any plate. All these factors can be studied. Let's see what are the results of these studies. So this was the kind of experimental setup which was used, and first let's study effect of intensity. So let's see how do we vary intensity, which is fairly simple. Intensity. So if I have particular source, monochromatic source of light, I hope all of you understand monochromatic source of light, and something like a sodium lamp, which emits yellow color, or we using prisms, we can separate. What happens if we move the source closer to the plate, intensity increases, and move it away, intensity decreases. So by changing the distance also, same light source, I can change the intensity. And let's see, if the distance is half, intensity becomes 4 times. We know that. Keeping the frequency of radiation fixed. How do we keep the frequency? Same color. Our common understanding is a particular color has a particular frequency, and we can adjust that. So what is done here, as we kept on changing intensity, and the photo current was measured. So here, for whatever current in the galvanometer, we measure the current. So we can, even if you don't know the frequency, I know of the distance, depending on the distance for same source, I can find out by what factor intensity is varying. And we plot, we find it's a linear relationship. Let's try and understand. Photo current directly proportional to intensity. And what is current equal to? Current is equal to rate at which electrons are getting emitted. If that's what current means. Current means net charge crossing a cross section. And net charge crossing is something similar to number of electrons getting emitted. The two things have to happen for current to happen. Electrons must get emitted and they must be collected. They must reach plate A. Both the things were happening, that only give rise to current. What are two things which have to happen for a photoelectric current? Jadip, what did I tell? What is that? What are the two conditions necessary for observation of photocurrent?
The electron needs to be emitted and has to be accumulated at the other plate.
And what is the name we use for this plate? I mentioned some name, collector plate. So the two things happen. It has to be emitted. It should not remain here. It should reach this plate. Then only circuit is completed. And this current. So what is the result we draw? So number. So if current becomes double, it implies we can naturally come to, we can infer the number of photoelectron emitted per second is also directly proportional to intensity. Both are something same. So here what you're assuming photocurrent is indication of rate at which photoelectrons are getting emitted or photoelectrons emitted per second. Let's see what is the other thing we study. Now, effect of potential on photocurrent. What does potential mean? I change the potential difference between C and A. So with reference to, if I call it 0, I can kill, if this is can be plus 2 volts compared to this. We are instead of potential difference. It could be something else also. We can vary the potential difference by some arrangement which is not shown here. But I have previous cases have seen how do we vary that part. Okay, so let's see that now. So this is the kind of shape. So the effect of potential of photocurrent, and we take positive potential at A. So when VA is greater than VC, that's called positive potential. That's the sign convention we are using. So if I have a DC battery, if I connect like this, it's a positive potential. Other way around, it will become negative potential. We'll study both one by one. So initially what we notice here, so what does this point indicate here? This point, vertical line indicates where this point, this side is anode potential, the potential of this point. So if when potential is 0, even at 0 potential also, if you don't maintain any potential, there's no battery connected. It's just a see this something. If both are at the same potential, even then we observe current. Electrons are getting emitted and without any force of attraction or repulsion. So you understand here, what does potential difference mean? See, potential difference implies if there's a potential difference, A is at higher potential, there has to be field. What is field equal to? Field is equal to potential difference divided by the distance, average field, and it is a uniform field. So potential difference between C and indicate field, and field will exert a force. So field, if it is positive potential, field will be like this. Field will be, if A is positive potential, field will be like this. If field is like this, which direction the force will act on the electron? Force acting on the electron will be in like this direction. So what we understand here, if we maintain positive potential, it tends to push electrons from the C side to A plate, C plate to A plate. So positive potential creates a field like this. It creates a force on the electron like this. So it accelerates photoelectron. It pushes electron from this side to this side. So what we find here, so as we increase potential, positive potential, initially slowly the current increased. Afterwards, current has become constant. And why the current has become constant? Even if you increase the potential level, see, only as many electrons can reach here as they are getting emitted. So in saturation state, the current or number of electrons reaching here cannot exceed the electrons which are getting emitted. So what dictates current? Current is dictated by electrons which are getting emitted. But what happens if suppose this is zero, if potential at A is zero? Let's try to understand. So I hope you understood. Positive potential means if VA is positive, field line is from positive towards negative. So field will be like this. If field is like this, force acting on the electron will be like this. It will accelerate. So positive potential involves accelerating potential difference. And if I make A negative, it will retard. So positive accelerating, negative potential implies retarding potential. Is this point understood? Kartikeya?
Yes, sir.
Positive, negative, are you clear?
Yes, sir.
No, positive potential leads to field, field leads to force. This force can either accelerate or it can retard. So positive means acceleration, negative means retardation. So if you understand, then you can understand rest of the part also better. Okay, so let's proceed further. So what do you notice here? So then reaches the state. So what happens initially, see, just think of it. The electrons which are emitted, some of them will be very lazy electrons. Lazy electrons means they receive energy which is just equivalent to their work function. They come out and they just they have very negligible velocity. So when there's no field here, those electrons, slow moving electrons, will just occupy the space and not move. And those electrons which accumulate here, we sometimes call it space charge. So if we do not have a pulling kind of force here, electrons will occupy space, and that makes it difficult for new electrons to come and move freely. So the reason why when we apply a positive potential, the current increase initially, because initially when we apply positive potential, it sweeps all space charge to A. That's what it does. So those charges which are just lying in the space, not moving, those charges also quickly reach. But once they reach here, afterwards its state is saturation. So how do you define saturation? With small accelerating potential. There is a space charge, slow moving photoelectrons occupying the space. They hinder the motion. They hinder the motion of electrons toward the collector plate. They hinder the motion of electron towards the collector plate. We apply small potential. Saturation current corresponds to state when all photoelectrons emitted at C reach collector plate. After that, it can, even if increase also, it does not lead to additional current. Only thing what will happen as you keep increasing potential, number of rate at which electrons are reaching will not change. Only thing they'll reach faster. They'll be reaching here with a higher kinetic energy. That's what accelerating potential will do. So that's the shape. So I hope you understand this part of the shape. So this part is positive potential. Now we come to what happens if I make this a negative potential. If I make negative potential, force and electron acting backward. It's when forces start acting backward with the negative potential is something similar to when we throw the ball vertically up, force acting downwards. What happens? It will move certain distance and be reverse. Are you understand? So the slow moving electrons may reverse like this if you apply negative potential. Faster moving electron will travel more distance, and very fast electrons only may reach here and come, and so then will happen. But once they reach here, they'll get collected. Is this figure understood? Tejas,
Yes, sir.
Tejas, are you clear?
Yes, sir.
Effect of negative potential. Here understood, the force will act in the retarding direction, and slow electron, if different electrons which are emitted have different kinetic energy, slow moving electron will travel a small distance and reverse. Little faster, travel more distance. Only the faster ones only which have adequate kinetic energy will reach the plate. So as I keep increasing this potential, lesser and lesser fraction of electrons will reach plate A. So what will happen? The current will keep decreasing. The current keeps decreasing. So retarding, when you apply negative potential, electrons are repelled, and only the more energetic or most energetic ones reach A. And hence the proportion of proportion of emitted electrons reaching A will keep declining, and the current will also keep decreasing. And then we come to a point where nothing reaches. What does nothing reaches? Let me try and explain what does nothing reach mean. So different electrons have different kinetic energy. There are certain smartest electron. This is one which is real hero among the electrons. Just like Tamil movie hero. No, Telugu movie hero, you would have reached anyway. Not Telugu movie hero kind of thing, but okay, small hero. It has a maximum kinetic energy. So this electron, which has maximum kinetic energy, until this point, it was able to reach the plate. But when we make this particular point here, even this electron also just fails to reach the plate here. It reaches up to this point and it works. So when this smartest electron or fastest photoelectron is not able to reach, what happened to a remaining poor electrons? This person gets maximum 90 marks, the next will get, others will get 80 marks only, 70 marks, nothing. They will reverse even earlier. Nothing will reach. So what is this particular point here? This particular point is called cutoff potential or stopping potential. This is the minimum negative potential for, which is necessary to make photocurrent zero. Why does the photocurrent become zero? What is the condition? Even the fastest moving electron also fails to reach this point. So if a negative potential, the potential at this point is zero, this point potential is minus V dot. So let's look at what will happen here. So in terms of energy, so we look at the energy of the electron. Here electron has, fastest electron has kinetic energy K, and this will be at this point when it emitted here, kinetic energy is K, and what is potential energy is 0. When it reaches here, its Ke becomes 0. It just fails to reach. And what is the potential energy of electron? Potential energy is equal to charge into potential. The potential energy will become equal to potential will become to charge into potential. This becomes equal to EV naught. So what is K equal to? See, when would it just fail to reach? When the maximum kinetic energy is just equal to E times potential difference. And this setup is a very smart way to measure kinetic energy of fastest electron. Yes, electron is something we cannot see, we cannot observe its speed. By using this setup, by equating, by just adjusting the potential to a value, it just stops the photoelectric current. What does this point imply? This point imply that even the fastest moving electron just fails to reach plate A. So if I apply this equation, it means the maximum kinetic energy or kinetic energy of fastest electron is equal to charge into potential difference. Is this understood? Shreya, have you understood this point here?
Yes, sir.
This graph you understood?
Yes, sir.
Okay. Yep. Okay, so this part, I hope, Khyati, are you clear?
Yes, sir.
Anvita, what is the doubt you have?
Could you repeat it, sir?
Okay. So, okay, let me repeat this point. Okay, so basically what you're looking at. So, Anvita, let's look at that part. But what you're saying here, the electrons which get emitted, they'll have different kinetic energy. Now, they all are getting emitted, they're not having the same energy. So, some will have close to little more than 0. And of course, if they have different energies, there'll be something like maximum kinetic energy. Is this clear? Okay. So, suppose the energy, it is equivalent to, suppose there are 10 people where I throw 10 balls up. If I throw 10 balls up with different velocity, one is 1 meter per second, 2 meter, 3 meter, 4 meter, 5 meter, 6 meter. Will they reach same height or will they reach different height? Anita?
Different height.
Different height. Which will reach the maximum height? Which will reach the farthest? The one which is having maximum kinetic energy will reach the farthest. So if I look at ball, this ball comes here, this ball reaches here, this ball reaches here. So if I look at this particular height, all balls are reaching. But at this height, practically nothing reaches here. So that is the level here. Something similar. Do you see similarity between balls being thrown against gravitational force which is acting against velocity and electron moving against which is this force acting here? I mentioned what is this force here, which is acting opposite to direction of velocity when it is negative potential. What is this F indicates, Anvita? Potential
Field,
difference. Huh?
nothing, sir.
Okay. See, if this has negative potential, which direction the field will act? This will have positive potential. The field will act from positive to negative side. This is the direction the field will act. Anita, are we clear about the field?
Yes, sir.
If field is acting, what is the direction of force acting on the electron? Force is negative, but since the electron is a negative charge, force will act like this. So it is equivalent to a retarding force acting when we apply negative potential. Okay. So in terms of energy, so when can I from here I can equate energy at point C to energy at A. Let's see how do we equate here. So energy at C will be equal to what? There are two forms of energy, kinetic energy and potential energy. So this point I am equating energy for fastest electron. Because in this condition, what is this condition here? Even the fastest electron is not reaching here. That's why there is no current. And very clear. So even the fastest
Yes,
electron
sir.
also. So let's write the equation. What is the Ke here? This is, I can write Ke max. And this point I take as zero potential, and this point is minus V naught potential. So this potential energy charge into potential zero. At this point, it reaches with zero kinetic energy, but potential energy is equal to charge into potential. Charge is equal to minus V, minus E, and potential is equal to minus V naught. It has EV naught. So I equate those two. What do I get here? Maximum kinetic energy is equal to EV naught. So this arrangement I can use if and is it possible to set? So I keep changing the potential. I can easily plot this graph. All I need to measure two things. I need to measure potential difference. I need to measure the current. If I measure those two things, I can plot a graph. I keep increasing the negative potential and keep measuring the current. As I keep increasing negative potential, as I keep increasing the repelling force, the current keeps decreasing and finally it comes to a stop. And this point is important point. We call it stopping potential. The stopping potential is minimum negative potential for which makes photocurrent zero. If I increase negative potential even further, even the current remains zero. So this is the minimum potential which is necessary to make the photocurrent zero. And this potential, this is a condition which is applicable. So indirectly, by calculating, by finding out the stopping potential, I can find out kinetic energy of fastest electron. Is that understood now?
Yes, sir.
Okay, good. So let's proceed further. And so what happens, suppose, so I have repeated this experiment with source kept here. Now, Anita, tell me what will happen if it's same source. Suppose it is a sodium lamp. If I move the sodium lamp closer, what will happen if I move the sodium lamp closer to the plate? What will change?
Maybe the force of the electrons will
Think of
change.
what will change if I move the source closer to the plate here. So think of all of you can think of what will happen if you move the source. But I'm not changing the color. I'm not changing the color. I mean the frequency of this is not changing. The plate also is not changing potential. So if I move the source closer to the plate, what will change here? Let me see who can answer. Isha, what will happen if I move the source closer to the plate? See. Which parameter will change? Okay. Bhagishri, what will change if I move this?
Increase, sir.
Huh?
Intensity is going to increase.
Intensity is going to increase. I mentioned earlier also, basically what will happen if I move it closer, intensity will increase. What does this graph indicate? So again, what we do afterwards, if I repeat the experiment, okay, I'll continue further interpretation. Intensity, this graph, I1, I2, I3. So this one, I2 is greater than I1. I repeated this experiment with higher intensity. But even with the higher intensity also, when I conduct the experiment, I find the stopping potential does not change. This I3 is even higher intensity. When I increase the intensity, the saturation current has increased. Does it make sense with increased intensity, the saturation current also increases? Does it sound logical?
Yes, sir.
Dhanshri, do you see a logic why with increase in intensity, why should saturation current increase?
Yes, sir.
Have you understood this graph?
Yes, sir.
Okay. Let's continue further. So if I have this observation, what conclusions we can draw, or what is the interpretation of experimental result? So this is something what you can observe from experiment. And having observed this, that's when we start making hypothesis, or that's what we start interpreting. See, since the current varies, it is a very simple interpretation to arrive at. Photoelectrons are emitted with different kinetic energy. So one thing is clear, that's why with different retarding potential, I get different value of current. So photoelectrons are emitted with different kinetic energy. One point we easily notice. With negative potential of V, only those electrons which have kinetic energy greater than EV will reach A. Rest will reverse this direction. So what will happen? So this also I hope I find it easy to understand. Photocurrent is zero when negative potential energy is equal to maximum kinetic energy. So most of the even the most energetic photoelectron just fails to reach A. So what are this point correspond to? What is this point corresponds to? So if I observe, you cannot observe fastest moving electron, but assume that you can observe fastest moving electron. What kind of path the most energetic electron will follow at this particular case? It will move and it will almost reach the plate A, but not, just fall short of this and reverse its direction. The force, repelling force, is able to stop even the most energetic electron. That's why the no electron is reaching this plate. That will become zero. So if you visualize this picture, I think this gives a good understanding. Even the most energetic electron just fails to reach A. So the potential which is applied at which even the most energetic electron fails to reach A is called stopping potential. And once we calculate the stopping potential, we can indirectly calculate the kinetic energy of fastest electron. So what is K max is equal to, which I mentioned previous case, K maximum kinetic energy or fastest kinetic energy is equal to E into V naught from conservation of energy. Okay. When the experiment was repeated with higher intensity, saturation current increased. Reason for saturation current increased because more number of free electrons are emitted, but the energy K max still remains same. So what it say when I make from I1 to I3, more number of electrons are emitted. But even in this case also, the energy of fastest electron remains same. So which means the energy of fastest electron only depends on the color of the source, not on the intensity. Maximum kinetic energy is a function of not intensity. It is only function of color. Color, we can say more better terms, color means it is only a function of wavelength and frequency. So it remains same for given frequency. So even if we change, so stopping potential for a given plate depends on frequency of the source, wavelength of the source. That was the interpretation from this question sheet. Then we move further. K max depends only on the frequency of light source material and is independent of intensity. Is this a natural conclusion from this graph here? All are clear up to this point? All are clear? Gayatri,
Yes, sir.
are you clear so far?
Yes, sir.
Hemant,
Yes, sir.
Joshua?
Yes, sir.
Okay. Okay, then we'll proceed further if you are clear up to here. And then what we do, okay, for with the so previous case, what we did, we didn't change the frequency. Then natural came, let's see how do we change, what happens if we change the frequency without changing the plate. Now, effect of frequency on stopping potential, keeping the intensity same. So we can keep the intensity same. So what we do now, if in previous case it was done only with yellow color, we can change with different frequencies. We can use violet color, we can use even ultraviolet. Ultraviolet will have even higher frequency than violet. So what do you do here? Keeping the intensity same, it is possible by adjusting the distance to keep the intensity same, but change the frequency. So this, it was repeated, let's say this frequency, it is new one is written, but I'll use F1 because it gets confused with B. So frequency F1, F2, F3, all this frequency, it was repeated. Since intensity was same, it was found the saturation current remained same. But as the frequency increased, the stopping potential increased. So can anybody say from this, for this is at a lower frequency, this was the stopping potential F1. F2 frequency being higher than F1, the stopping potential was greater, and even higher frequency even greater. Can somebody tell me what do we conclude from this? Anybody would like to make a statement to drawing an inference from this?
Energy of the electron depends on the frequency of the source.
And also, higher the frequency of source is, greater is the energy of fastest moving electron. Is it not? That's what, and that's what depends. So same, so different saturation current, same saturation current, but different stopping potential. Higher stopping potential, higher frequency, implying higher Kmax for higher frequency, hence requiring higher retarding potential. This is a natural conclusion we can draw from experimental results. Okay, so now we do, okay, so this is something, so this was only for one same material. Then the natural question come, what happens if I use a different material? Well, what is the frequency, what is the, so what we find here? There's a relationship between F1, V1, F2, V2, F3, V3. It's a relationship between frequency and stopping potential, and stopping potential is same as Kmax. Understand, stopping potential and Kmax are related. So this is for the same material. What happens if we use different plates? Aluminium, then copper, then cesium, then platinum. Now we can do that. We can change the material as well. Okay, so what we marry here, V naught varies. Then in the, if we do so, this was the shape here. Suppose I take a metal plate A. So I plot. Okay, so in this case also, this graph is for one plate. This graph is for a different plate. So when I see this graph, it's like a linear curve, and it starts from here. So what is this point? If I say here from metal plate, what can I say about this particular point? Anybody would like to make? What is special about this point here? What is zero at this point?
Stopping potential.
The stopping potential. Okay. So at this point, whether this certain frequency, this is this, and as the frequency is increasing, the stopping potential also is increasing linearly. That is the interpretation I can draw from this graph. Okay, and for a particular frequency, for there's a particular minimum frequency when the stopping potential becomes zero. It means even at the zero potential also, there's no current. What does this point imply? This point by zero stopping potential means I'm not trying to stop it. Still, electrons are not reaching. What can we conclude from that? There's no repelling force. Still, there's no electron reaching the plate A. What does it mean? What could be the reason? This point means the stopping potential is zero. I'm not trying to stop it, but still electrons are not reaching. Why it could be? What could be the reason why it is not reaching? Because not getting emitted. So here zero stopping potential, but there's zero stopping potential, and still no current implies what? Even with no repelling force, current becomes zero. Stopping potential means current has become zero. With zero potential also the current has become zero. It implies electrons are not emitted at this frequency less than this. At V naught frequency, or I can say F naught here, we'll use F because V velocity gets confusing. At this frequency, no electrons are getting emitted. If I lower the frequency even further, no emission of electron. I need a minimum frequency for metal A for photoelectric effect to start. Similarly, for other metal B, I'll need a higher minimum frequency for photoelectric to start. So this is the frequency at which photoelectricity starts. This is the frequency which is necessary to impart enough energy for photoelectric to start. Afterwards, if we keep increasing frequency, then stopping potential keeps increasing, because as I increase the frequency, the kinetic energy of electrons also keep increasing, hence stopping potential also keeps on increasing. What is this point here? Minimum frequency required. This is the minimum frequency at which photoelectric current stops. The frequency has to be greater than this. That's the observation. And this value is different. What is the minimum frequency required for photoelectric effect to commence? So this point, if I have to say, what would I say about this point? Minimum frequency for photoelectric effect to take place. And can you think of any logical explanation why it happens? So below this, what is happening? Below this, what happened? Energy which is contained in the light is less than work function. If energy contained in the light is less than work function, no photoelectric emission will take place. So let's look. So this graph is what? This graph is again an observation from experiment, and again we interpret. What does it imply? Okay, there exists a minimum cutoff frequency for which stopping potential is 0. So, okay. So what we notice here now, so if this is just read the statement, even at a very low intensity, but frequency greater than f0, it triggers photo emission without any time lag. So if I look at this, so if I have a light source which have very low intensity, I have kept the light source very far, or the power consumption of the source is very low. So just for example, so I have very feeble violet color source. Immediately homostatic nanosecond immediately leads to photoelectric effect. Whereas if I use red color, very bright and very powerful red light, also no photoelectric effect. Why? This frequency is greater than threshold frequency. This frequency is lesser than threshold frequency. Is this understood? There's a threshold frequency. If frequency less than threshold frequency, no photoelectric effect takes place, whatever may be the intensity. If frequency is greater than threshold frequency, photoelectric effect takes place immediately, even for very low frequency. Immediate, without any time lag, that's an observation. Okay. And based on all this observation, when we have all this observation, then you make a theory. What kind of theory explains all the experimental observations? So based on whatever you have seen here, all those things were captured in form of Einstein's photoelectric equation and some other hypothesis. We'll go through what is the hypothesis. Okay. So again, to repeat, let's say some of if you're not clear, what is the unit I use for frequency? Jaideep, what is the frequency I'll use for frequency? Something like this. Okay. So suppose for a metal, if frequency is 10 to power 6 hertz. So if in this case, if I use a light source which has a frequency of 0.5 into 10 to power 6 hertz, will I observe any photoelectric effect here? How do I observe photoelectric effect? In terms of current, no photoelectric effect. But if I use a frequency, this f1, nothing happened. And suddenly if I use f2, which is something like 1.01 into 10 to power 6 hertz, what I notice, immediately, even the light source is very feeble, immediately I see a small current here. So what does indicate? He understood this point, because in this case, minimum frequency required to initiate photoelectric effect is this. And as I keep increasing, it will require very small stopping potential. But if I use third source, something like 2 into 10 to power 6 hertz, in that case, what will happen? Compared to this, this will require small stopping potential. This will require a larger stopping potential. You understood from the figure also? Understood. This one, first one, what I was saying was something frequency here. Frequency just greater than threshold frequency, very small potential. As I keep increasing the frequency of light source, okay, the stopping potential will keep on increasing in the linear fashion. The graph is linear. Okay, that's now correct. He wrote in very simple way, and his sign is surprisingly so simple. And for this work, actually, Einstein received a Nobel Prize for this work here, photoelectric effect. What a simple way. What he said, okay. So this is something basically the light will come to the photon theory also. He said light is composed of what you may call as energy packets, kind of thing, photon. So light is composed of photons, okay, and for different frequencies, photons have different energy. As the frequency keeps increasing, energy of photon also keeps increasing. So you can calculate. We'll come to photon theory later. So this energy of photon is h into frequency. So energy of photons, so when the light incident, and it is equivalent to photons striking a certain energy. And here this energy transfers take place. We just equate the energy. What is energy? Energy of photon partly goes into work function. If energy is greater than work function, remaining part comes as a kinetic energy, Ke max. So this condition apply if this equation is applicable only in case of fastest electron. So why other electrons have lesser kinetic energy? Many electrons, after they receive energy from the photon, they may undergo subsequent collision and they lose their kinetic energy before they come out. So those electrons which do not lose any of the energy they have received from photon, they come out with maximum kinetic energy. Which kind of, so are we clear? which case do we get electron with maximum kinetic energy? Abhirup, what is the condition for maximum kinetic energy?
Where it does not lose energy in collisions.
Non-collision. Entire energy it has received from photon, it has used for work function, and remaining part, no energy is lost in subsequent collision. It comes out with the remaining kinetic energy. Rest of them, as
What
they
exactly does it
some of them
collide
lose a higher fraction, so they will vary. So energy, kinetic energy of all electrons will vary between 0 to k max. Okay. So this is a very simple equation. Energy of photon is equal to work function. And using this principle, again, if you go back and try and study each observation, each experimental result, all can be explained. And what is K max? K max is equal to E into V naught, which is stopping potential. That's an important thing we need to understand and remember also. So how do I write this equation? Energy of photon is h into frequency. All of you would have done this Planck's constant. Does anyone remember what is value of Planck's constant? You would have done in chemistry also.
6.65
6
into
point,
10
okay.
power.
So all of you remember this is a Planck's constant, and most cases we are not required to remember, but since it is so commonly used, if you remember, it's better. I'll use something else in place of Planck's constant. So if a frequency of source is known, Planck constant is known, we can calculate energy of each photon. So either HF or HC by lambda, both are similar. So energy of photon, this is the term we use to indicate work function, and is equal to this K max. All this function, if I use SI unit of Planck's constant, this entire equation will come in joules. But if I want to convert, because this is too large a number, if I divide joules by E value, it gets converted into electron volts. So if I divide this equation by E, I get my energy equation in electron volts, which is more commonly used. So what I'll do now, I'll divide this term. So this is very simple equation. This is just like a conservation of energy for electron, which has not lost any energy during subsequent collision. So if I divide by E, everywhere I just divide by term E here. But in this case, what is written here, this term phi, work function, rather than defining in terms of volts, it is normally itself is defined in terms of electron volts. So there's no need to divide by E. This is already in electron volts, and divide this becomes V naught. So that's the equation. So most of the numericals are just based on this equation. So numericals related to topic of photoelectric effect is based on Einstein equation, which is a fairly simple equation to use. Okay. So energy of photon, how would I calculate energy of photon in electron volts? There's a simpler simplification. So suppose I have to calculate, I would have calculated 6.63 into 10 to power minus 34, and if suppose in wavelength, then into 3 into 10 to power 8. And if wavelength is in nanometer, many times you take wavelength in nanometer. If wavelength is by nanometer, I need to convert into meter. And then if I want, this is in joules. To convert into electron volt, I will divide by 1.6 into 10 to power minus 90. So this all put together, it comes roughly equal to 1242. So this is a method I would use not only in this chapter, remaining chapters also. Whenever you have to calculate energy of photon or EM radiation in electron volts, it is roughly equal to 1242 divided by lambda in nanometer. And some people, if you have to use in Armstrong, and 1242, or actually many times you use only 1240 itself. 1240 is a good enough approximation. So let's understand what it means. If I have a light which has a wavelength of 620, if wavelength is 620, it will have, each photon will have an energy of 2 electrons. Or if I have a light source which has energy wavelength equal to roughly 413 nanometer. If this the wavelength is energy would be roughly 3 electron volts. And this actually is more or less the range of visible spectrum. Visible spectrum start from something little less than 2 and extends to a number little greater than 3. So we can, this easy method to calculate. So rather than using this number, this is something which you need to memorize. 1240 divided by lambda. And in terms of Armstrong, this is nanometer. If it is Armstrong, this Armstrong is 10 to the power minus 12. So it will become 12,400 divided by lambda in Armstrong. Armstrong is 10 to the power minus 10 meter. Okay, that's how we'll calculate. So this term is easy to calculate. If wavelength is given, I can calculate what is the energy in terms of electron volts. This term we have seen earlier also. For many metals, it ranges from 2 electron volts to something like 5.6 electron volts. And red color, see, which will have lesser energy? Red color has energy less than 2 electron volts. So what it means, if I use a red color light is not having enough energy to produce photoelectric effect. So energy of the photon, and that's why it will fall below the threshold level. Okay, so this is a point we'll remember. So either 1242, I think most cases 1240 is good enough. 1240 by lambda in nanometer, so many electron volts, that's energy. So what is threshold frequency? In case of threshold frequency, if I use a light source which is just equal to threshold frequency, it will start photoelectric effect. But what is the kinetic energy of electron emitted? Maximum kinetic energy also slightly greater than 0. So if I have threshold frequency, the stopping potential is close to 0. That's the definition of threshold frequency. So if I substitute threshold frequency and threshold wavelength, let me first put threshold wavelength. So in place of lambda, this equation, I am substituting in normal SI equation. HC, frequency lambda naught indicate threshold wavelength, and F naught indicated threshold frequency. In that case, stopping potential will be 0. That will be equal to work function. So at threshold frequency, energy of photon is equal to work function. That's another way to express work function. The work function can be expressed in terms of threshold frequency or threshold wavelength. And for photoelectric effect to take place, frequency has to be greater than F naught, or wavelength has to be smaller than lambda naught. It comes in the denominator. So it has to have minimum frequency, or it has to have particular maximum wavelength. It is defined in terms of maximum wavelength or minimum frequency. Okay. Then there are simple numericals, so I will not start numericals. We will do numericals in the next session. All these numericals are part of assignment. So when we have evening session or 3 o'clock session, we'll go through this question. You'll find most questions are based on this simple equation, and we should be able to solve them without any difficulty. So I will send this sheet. This is all part of home assignment today, and this all we'll do in the next session. And if